Let's look at an application of the third law of thermodynamics. Remember, the third law defines absolute zero, a temperature scale where it's 0 degrees is actually the lowest possible temperature. There are no negatives in an absolute scale. The absolute scale that we use in science is the Kelvin scale for measuring temperature. Now, the difference between 1 degree and 2 degrees in kelvins is the same as the difference between 1 degree and 2 degrees in Celsius. So it moves up by the same amount each time. But it's shifted down by 273 degrees so that its zero lines up with absolute zero. So on this simulation, this is actually a simulation that's supposed to show the ideal gas law, so you can play around with this if you want to see those ratios between pressure, volume, and temperature and things, but we're just going to use it to look at temperature. I've got oxygen molecules sitting in here at 8 degrees Kelvin. That is an extremely low temperature. I can lower it even more by using this bucket. It puts ice in there, so it pulls energy out of that system, and we can see that the temperature is getting lower and lower. Now we're at 1 degree Kelvin, and 0. So you can see, if you look at that again, 0 degrees Kelvin, as soon as it hits 0 degrees Kelvin, all movement in these molecules stops. If I give it even a little bit of heat, just a little bit, now we're at 5 degrees Kelvin, we can see there's a little bit of movement here. These particles are vibrating around, even though at this temperature, oxygen, pure oxygen, is a solid. So this is a solid. We can see that they're all lumped together, sitting in one pile, but they're still vibrating just a little bit. This is happening to the molecules of everything you interact with. I mean, think about it. The computer that you're working on, the table that you're sitting at, or your bed, more likely if you're still getting up for the day, all of those things are going to be at room temperature. But the molecules inside of those are going to be moving around just a little bit. And there's so many molecules that we just don't notice this tiny little movement. But it is there. Now if I increase the heat, look at that, it moves up pretty quick and something starts to happen. When I reach a certain temperature, this solid stops really being a solid. It starts to fall apart. And then it's starting to turn into a liquid and then into a gas. There's a very short while that oxygen is sitting as a liquid. But if I want to, I can pull out all that energy again, watch the temperature falling, and steadily those particles, they don't vibrate as much, they don't move around as much, they're steadily slowing down. And if we hold this long enough, we would get back to absolute zero, where it's going to be a solid, a perfectly ordered solid, where there will be absolutely no movement. I'll post a link to this simulation so you can go ahead and play around with it yourself. You can move around the temperature, pressure, all of the things. You can add more molecules in. If I add more in, it'll actually increase the temperature because they're bringing more motion into that system. I would have to take all that temperature back out. You can change this from pure oxygen to argon or neon or water molecules.